So what I want to do is I want to talk a little bit about canonical form. So does it matter what letter we use for variables when we integrate? No. Could I have my variable be a smiley face? Yes, I could integrate, smiley face cubed, d smiley face, right? Is it still recording? Okay. So I could integrate something like this. People would laugh at me, or maybe they'd smile at me. This is perfectly fine. Why don't we do this?
It's annoying.
It's annoying. It looks stupid, right? We want to have a good choice of variables. Something that's descriptive when you look down. If you have a function little f, what do you use for its antiderivative? Big F. That way, when you quickly glance down, you can see, oh, there's a relation between these two things. The name has meaning. Again, I could call it anything I want. The worst physics book I ever saw used P equals mf to stand for force is mass times acceleration. I put the book down within a minute as soon as I saw that. Okay? Notation has meaning. What we're going to do right now is we're going to take all the linear programming problems we're looking at and we're going to put them in a canonical form. There's not really a need in some sense to do this, but it allows us to use one technique to handle all linear programming problems because they're all put into the same form. In the old days when people were trying to solve quadratic cubic quartic equations, they didn't like negative signs. So they wouldn't have, polynomial equals 0. They would have all the positive terms on one side equals a bunch of positive terms on the other side. And then you'd have all the special cases. The quadratic equation when all the signs are positive. The quadratic equation when the x squared and constant term are positive and the x term is negative, so the x term goes on the other side, and you're playing all these games. And if you think about things representing different regions, this is an area, this is a length, it kind of makes sense to do something like this, but it means you have to develop different techniques, you have different types of input. We're going to put all linear programming problems in the same way. So for us, it's ax equals b, the components of x are greater than or equal to 0, and we want to minimize x transpose c. So for us, this is the canonical form. So why is it linear? It's linear because we're minimizing a linear combination of the unknown entries. Right now, we will assume the entries are real numbers, and we have something in the form ax equals b. So the only difference between this and linear algebra is the constraint a little bit on the solution space, but that's not a big deal. We can solve a problem in linear algebra and then just say, does our solution have no negative coordinates? But it's now, in addition to solving a linear problem, a linear algebra problem, we're also requiring a quantity to be minimized. And that's the big difference in linear algebra. Now, typically, do you think this is going to be an overdetermined or an underdetermined system? I'm sorry? Undetermined. If it was overdetermined, there's at most one solution, and then you don't really need to develop a subject. You just use linear algebra. So generally it's going to be underdetermined, which is good. That means you have options. And then the goal is to figure out which option is best. So there's a bunch of things hidden here. The first thing is that we have equality. So equality is not that bad. So imagine we have, a11 x11 plus a1n x1n is less than b1. I then just add another slack variable to make them equal. So I introduce a new slack variable. Introduce slack variable. And now once I introduce the slack variable, now I can force an equality. And then if I don't really care about what that slack variable is, then I'm in good shape. Are there any constraints we want to have on that slack variable that we're introducing? Yes? Greater than or equal to 0. If I made it negative, if I introduced a negative slack variable, then all of a sudden, oh Lord, I could push this above b1. So a slack variable that is non-negative. Great! We're only looking for solutions where the components are non-negative. That fits in perfectly. So this handles the case when we have a less than sign. What if we had a greater than sign? What would we do? So one possibility is we could introduce a variable on the other side. We could multiply by -1 first and then do this. So if greater than 0 or greater than b1, multiply by -1 first. I kind of prefer doing it like this because it reduces me directly to what I've just done. And you know, I believe mathematicians are fundamentally lazy in a good way. And whenever possible, you want to reduce to something you've already done. So we can now handle the case of greater than, we can handle the case of less than. Okay. The next constraint is that all the components are non-negative. And maybe in the real world this is not physically reasonable. You could have maybe upper bounds for the x's. You could have lower bounds for the x's. So how do we do something like that? So imagine you want x1 to be less than, I don't know, some constant alpha 1. How would we do that? So I want to have, maybe I have this, my variable is maybe not initially going to be greater than or equal to 0, I just want it to be less than alpha 1. How would I handle something like
that? Just do the calculations normally, and then if it's a problem, then think about it.
Well, we want to put in canonical form. We don't want to have to do the calculations. That's the whole point of canonical form. We could put this as a constraint. Right? If I put this as a constraint, I let x1 range freely, but if I add that to my list of constraints, that will force x1 to be at most alpha 1. And then do we know how to handle a less than? Sure. So, make a constraint. Similarly, if we wanted x1 to be greater than alpha 1, no problem. What if we want x1 to be any real number? What if we don't want an upper or lower bound? I can't put infinity in as a symbol. As much as my kids say they love me infinity times, we can't work with something like that. How would we deal with that? So, want x1 in I. You write x1 equals what?
Single term variables.
Excellent. y1 minus z1 with y1, z1 greater than or equal to 0. So this is a beautiful trick. You give me any real number, I can write it as the difference of two real numbers. And I can assume these two real numbers are non-negative. Now I'm in excellent shape. And so it's really not that much of a restriction to say I want my x's to be greater than or equal to 0. Now in a lot of the problems you're looking at, it may not be the most natural way to phrase it as I want my things to be greater than or equal to 0, but it allows us to, when we're doing the theoretical analysis, when we're setting things up, to assume that our linear programming problem is in a certain form. And because it's in a certain form, we know we can manipulate things in a certain way. So this allows us to put a linear programming problem in a certain canonical form. Okay, any questions about this? Okay, so this is the first part. The next key ingredient we need is the concept of duality. And so I made a nice video a few years ago with OIT. Not even close to going viral, but it's still a fun problem. Right? How many of you have played tic-tac-toe? How many of you played chess? Right. So we're going to play a game of chess. I think we've already talked about tic-tac-toe in this class. We'll keep hitting all the games you've seen. Except due to budget cuts, we can no longer afford the standard board. So we have a 5x5 board now. Okay? And the goal is we have 5 queens and 3 pawns. And I want to place the 5 queens on the board in such a way that I can put 3 pawns on safely. Now what's interesting about this is the thought process you use to try to find the solution. One thing is, what is the best place if you're only putting down 1 queen to put the queen in terms of maximizing how many spots are safe for pawns.
A corner.
Yeah, I think putting a queen in the corner is probably the best. And so one thing you would say, well, let me do, these as my first 4 moves. Boom, 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 boom. And now 4 squares are left over. Right? And so the question is, where can you, is there any way to put a queen? Well, if I put a queen here, it's going to kill those 2 squares. If I put the queen here, it'll kill those 2 squares. Here, it's going to kill those 2 squares. You can quickly see there's no place to put the remaining queen. This is a great philosophy that what's locally best is not necessarily globally best. If I'm just putting the queens on one at a time, at each stage I could say, what's the best place to put this queen down? And that's not going to lead to the optimal answer. Now, I mentioned tic-tac-toe for a reason. It's not because I forgot what I was supposed to lecture on. How many opening moves are there in tic-tac-toe? 3, right? Tic-tac-toe has 3 opening moves. 1, 2, 3. How many places are there to place the first queen?
6.
6. So there's really only 6 opening moves for the first queen. 1, 2, 3, 4, 5, 6. And so if you're trying to figure out what's the best way to put down the queens, well, I can say there's only 6 initial moves, and then depending on my initial move, I have some symmetries to try to find the next one. And you can keep going. So if you haven't solved this problem, you know, one of your homework problems is solve this problem, find the best way to place the queens. How many possibilities are there for putting 5 queens on a board? Let's assume we don't consider this square different from this square. Because sometimes with computers, it's better not to take advantage of the symmetries. It's more of a pain to actually program than to just solve it by brute force. How many ways are there to put down 5 queens? 25 choose 5. So we have 25 squares, 5 ways to choose them. That's how many ways we can throw down the queens. You know, label the squares 1, 2, 3, 4, 5, all the way up to 25. Choose 5 numbers, and then just for each configuration, check and see how many places are safe for a pawn. 25 choose 5 is not horrible, it's definitely doable. But if the board started to get larger and larger and larger, this would quickly reach the point where it would not become feasible anymore to do the computation. There's a better way to look at this problem, a new perspective you can take. Any thoughts on the new perspective? Yes?
Look at the pawn, where to put the pawns.
Yeah, I'm sorry?
Look at where to put the pawns.
Yes. You know, rather than focusing on, I want to put down 5 queens, put down 3 pawns. Or if you want, if you really like the idea of killing pieces, put down 3 queens so that 5 pawns are safe, and then flip all the queens to the pawns. So the idea is to solve the dual problem. Solve dual problem. You know, place 3 queens so that 5 pawns are safe, and then send the queens to a pawn, the pawns to a queen. For those of you who've seen quantum physics, this has absolutely nothing to do with the operators there. Right? Computationally, how many ways are there to place 3 queens on the board?
25 choose 3.
25 choose 3. That's an improvement. You know, you're saving roughly 20 squared over 5 times 4. So you're saving roughly a factor of 20, just as a ballpark estimate. That's not bad. And so this is the principle of duality, that sometimes the problem you want to solve, it's better to solve a related problem first. A great example of this is if you've taken advanced analysis, if you've seen something called Poisson summation. It's a great situation where you pass to a related problem and you can often pass back and forth. I'm not going to go into too much of the duality here. You can read about it in the book. Given a canonical linear programming problem, there is a dual problem you can consider. And what's nice is there's a great lemma that says if you are a solution of the dual problem, that gives you some information about the solution to the original problem. And then the question is, what do we mean by a solution? A solution means we just satisfy the constraints, we don't worry about how optimal we are. So this is one of the great advantages of this idea of approach. So I'm not even going to write down any of the details, but we say X is a solution to the canonical linear programming problem if AX equals B and X is greater than or equal to 0. And then you want to try to minimize C transpose X. And you get C transpose X is going to be related to bounds from the dual problem. Is related to bounds from the dual problem. So what happens is, you look at a related linear programming problem, essentially replacing A with A transpose, essentially replacing B with C, and you find a feasible solution there. You find something that satisfies the conditions, and that gives you an upper bound for C transpose X. Oh, sorry, a lower bound. So it gives you a lower bound. It'll give you a lower bound for C transpose X. So gives a lower bound. Well, if you have a lower bound, what happens if you attain the lower bound? Then you have to be an optimal solution. I know every feasible solution is at least going to contribute this much. If I find one that actually contributes this much, then it must be optimal. If it contributes more, it may be optimal, I don't know. So one of the things that's nice about this is even if you can't solve the problem, you can often tell how close you are to optimal. And you might be close enough, oh, I'm a multi-billion-dollar company, I'm off by $10,000. I can live being off by $10,000, in a multi-billion-dollar industry. Especially when you consider the fact that for these, big corporations, you don't know the actual values of the parameters you're putting into the model. So to insist on an exact solution to an inexact model, to me, doesn't seem reasonable. So this is the power of looking at the dual programming problem. It gives us some idea of how close we are to optimal, and we can use this to try to keep correcting. And then there's some beautiful theorems in linear algebra about this stuff. Any questions on this part? Now, I didn't even talk about this earlier. I just said that our goal is to minimize. If we wanted to maximize instead of minimize, what would we do?
Negative.
Yeah, we replace C with negative C. So really, if you know how to find maxima, you know how to find minima, and vice versa. You might as well choose, we're in the subject of minimizing. So if you think about it from a business point of view, you're trying to minimize cost rather than maximizing profit. Okay. So let's do one of the most famous linear programming problems. And I think I sent you a story by Danzig about when he tried to apply the diet problem and solve it, and the different recipes he was sending his wife. There were this ridiculous amounts of, I think, vinegar, among other things. And so, this is one of the early successes of linear programming. So imagine you're the supreme dictator of North Korea. Hello. You don't really care too much about your people. You want a certain subset of them, I think, to stay alive, but I think you're quite happy with the subset. You want to keep them as fed as cheaply as possible. You don't really care how much they're enjoying the meal. What is the cheapest meal that will keep them alive? So for simplicity, let's assume there are two products. And I don't care what the numbers are. Anybody want to give me two foods they like?
Hot dogs and hamburgers.
Hot dogs and hamburgers. And I need two nutrients. Fat and protein. So I don't care at all if the numbers are even remotely reasonable. Right? How much fat does 1 unit of hot dog have?
Like 50% every feeling that.
Well, I need a unit amount. 10 units. And how much protein? 5. And how much will one hot dog cost you?
$1.
$1. How much is a hamburger cost?
$1.50.
$1.50?
$2.
$2.
Sorry, I'm just lazy picking round numbers.
Yeah, pick round numbers. Well, if you're picking round numbers, you'd pick like 0 or 8. Alright, so we'll pick $2 for hamburgers. How much?
That's funny.
Thank you.
I laughed preemptively because I realized it.
Did you ever see the TV show Press Your Luck? Just speaking about laughing preemptively. There was a contestant back in the 1980s who recorded a bunch of shows on his VCR, and he noticed that as the lit square is going around the board, it's not going around randomly, and there was a pattern. And so he knew when to hit the buzzer, and he was smiling and cheering before it stopped. And so, I mean, at first the show refused to pay. Eventually they did pay him the $100,000. It was the largest, single-day winnings in American TV show history. It was years before they would re-air the episode. But it was a great example of preemptive, enjoyment. But how much fat does a hamburger give you?
25.
25. Okay. And let's say it gives you 15 units of protein. I want to minimize my diet. What's my diet?
All hamburgers.
All hamburgers, right? As soon as you tell me this, 1 unit of hamburger, $1 worth of hamburger would give me 12.5 units of fat and 7.5 units of protein. In a situation like this, I would never want to have any hot dogs.
So this is more than double of both, and yet.
It's more than double of
Exactly
both.
double of both.
Now, the only way you might have hot dogs is that if you can't buy, a continuous amount of hamburger. So this may not be too appealing, but think of the, hamburger thing that's being squirted out for your meal. Okay? Okay. Well, for hot dog, that's almost how they do it.
Yeah.
Yeah, I know. I realized that when I said that.
Yes. How many of you have seen Father of the Bride?
Yeah.
Steve Martin.
Yeah.
He goes berserk because hot dogs and hot dog rolls are not sold in the same number of units.
Yeah.
And he's paying for so much stuff for the wedding, he starts opening up hot dog rolls and throwing out hot dog rolls so that they now have the same unit count. Alright, we're not going to worry about issues like that now. That's for later in the semester when we get to integer linear programming. So clearly, we don't want to have 15 units of, well, we might want to, but we're not going to have 15 units of protein. Or the problem is just not going to be interesting. How many units of protein should we have?
7, between 5 and 10.
Between,
Like, it shouldn't be less than double.
it should definitely be less than double, so it's got to be less than 10.
Can you make less than 5?
We could even make it less than 5, we could make it 2.
Okay.
So, hamburger is a great source of fat, but a horrible source of protein. Okay? And so now when you look at this, it's not clear what's the best thing to do. Because if I double the hot dog, I'm great on the protein, but not so great on the fat. And so, how much fat do I need a day to stay alive?
50.
50? Recommended daily allowance. And how much protein?
12.
12. So again, depending on the numbers you put here, that's going to affect how your answer is.
We're gonna be fat people.
Yes.
Fat and not strong.
This is why I decided not to bring the M&Ms today. I figured with this lecture, this is not the day to bring out free food. Or at least free food like that. So what we want to do is we want to figure out what is the best. So we have constraints. So imagine we have x1 units of hot dogs and x2 units of hamburgers. If everybody's stomachs can bear with this, what can you say about the quantities x1 and x2? Yes.
Greater than or equal to 0.
Yes. If you want to try to imagine what it would be for x1 or x2 to be negative, I will leave that as an exercise to the reader. Okay? Sorry, it's supposed to have to say reader. I will leave that as an exercise to think what it would mean for x1 to be negative. We will not deal with that case. It is quite reasonable to assume x1 and x2 are non-negative quantities. Okay? So I'll move this over. 25 to x2, 10 by x1. So here's right. x1, here's x2. So my feasible space is all points in the x1, x2 upper right quadrant. And now I have a bunch of constraints. The first one is x2 is non-negative, x1 is non-negative. So that means I'm up, in this region here. The second is x2 is non-negative. That's over here. So those are my first two constraints. x1, x2, greater than 0. Now the next one is 10x1 plus 25x2 equals 50. So 10x1 plus 25x2 equals 50. So if x2 equals 0, x1 equals 5. If x1 equals 0, x2 equals 2. So I get a line like this. The next constraint is 5x1 plus 2x2. I think you meant to say 10 here.
Sure.
Equals 10. And so now when x2 equals 0, x1 equals 2. And when x1 equals 0, x2 equals 5. Now, I have a mistake in these constraints. What is the mistake? Yes?
They should be greater than or
These should
equal
actually be
signs.
greater than or equal to. So I'm not putting things in canonical form.
Yeah, but if it's an optimal solution that you're looking for.
If it's an optimal solution, because we can have things in a continuum.
Right.
So that's an interesting question. Will the optimal solution have them both equalities?
Because you're trying to minimize, you always have a problem when you're trying to minimize what you're giving. So
Okay. So does everybody agree that in an optimal solution we will have two equalities?
Well, I mean, it depends on whether we're assuming that compounds are continuous or discrete.
What if I had this? 1 unit of hot dog gives me 100 units of fat, which I think is more reasonable, and 5 units of protein. Alright, what's the optimal solution? Hot dog dominates hamburgers now. I would buy 2 units of hot dogs. One of these will be an equality. Because if they were both greater, I could cut back on something. But I don't know that both of them will be an equality. So it's actually possible that one of them might be an inequality. So I have a space that looks like this. And so it's anything in that region is a candidate solution. Anything in that region is feasible. It will keep me alive. I know some of you should remember Calc 3. If not, this is going to be bad for the people who have you as graders. How do we find maximum and minima in a region like this? What do? Endpoints, the boundary, and what else? We look for the derivative. We look for critical points, places where the derivative is 0. Well, we don't have differential calculus here. We have the same idea. So let's look at our last thing. Our cost is going to be x1 plus 2x2. And let's call that C. Upward sloping or downward sloping? Down. I can write this as x2 equals negative 1/2 x1 plus C. So basically, all the points x1, x2 that give you the same, that give you a diet of the same cost would just be a straight line. This would all have one cost. And then let's call that cost, C0. That would be C1, C minus 1. I don't know what those numbers are, but all of these points would have the same cost. So this is where the geometry of the subject helps us enormously. If you're at an interior point, can you be at an optimal solution? No. One of the directions should decrease. So you keep flowing until you hit a boundary. What are the possibilities when you hit a boundary?
Seek it.
You could hit a vertex. So there are 3 vertices you could hit. What else could you do?
You can hit one of the lines.
You could hit one of the lines. There's 2 ways to hit a line. One way is to hit exactly with the same slope. Now if that's the case, you're then indifferent to all of these points. Or what's more likely is you could hit it at some angle. If you hit it with the same slope, you're indifferent. So you might as well say, let's go to a vertex, because you're indifferent between all those points. If you hit it at an angle, again, you just keep flowing until you hit a vertex. So no matter what, you always flow to a vertex. So there's really only 3 places to check. Absolutely amazing. Only 3 diets are really under consideration. Now what would happen in the real world? Well, in the real world, you would have hopefully more than 2 foods. And there are almost surely going to be more than 2 nutrients that you need. So the geometry becomes a lot more complex. So just because you flow to the boundary, it helps you. You go from infinitely many points to finitely many points, but if the finitely many points is too large of a number, it's not going to be practical. You need a way to efficiently check all the different points. Okay. In Calc 3, how do we check points on the boundary?